Hey everybody, Mike Stewart here again. Hope everybody's having a good weekend or a good week now that you're here. It's Sunday for me, probably a lot later in the week for you guys. A lot of people haven't done much of the Blackboard assignments, and I know the people that are listening to this right now are probably the few that are actually doing the assignments, but the end of the semester is going to come really fast, and if you get behind, it's going to be really hard to get caught up. So try to stay on top of this stuff. As soon as I post this stuff on Blackboard, like get it done and get it over with. Without face-to-face, there should be at least 8 hours a week of your lab times that you could devote to Blackboard and getting caught up. So anybody needs help getting caught up, or if you're confused or you just don't get it, like let me know. Reach out. I'll help you out. That reminds me, we only have what, 4 weeks left? It's going fast, you guys. Okay, so today we're going to learn about igniters, pilots, and flame sensors. So up until now, we talked about the sequence of operation. So thermostat calls for heat. The control board goes into a self-check. Draft inducer comes on. Now it's drawing a negative pressure, like a suction, if you will, through the heat exchanger, across the burners, and from our inlet pipe to outside. Okay, it's like a big straw or a big, like a hose on your shop vac in your garage or whatever. So that's happening, and then we prove that that's running with a pressure switch. Okay, the pressure switch says, oh yeah, I sense that there's a negative pressure in my heat exchanger, so that means that it's running. The inducer is. So then from there, the igniter is energized. And we ignite the flame, the gas, we ignite it many different ways. There's more common methods today than there was, say, 20 or 30 years ago. And so we're going to go into that, and bear with me, like watch this whole video before you, because it can get really confusing, and before you like give up or get frustrated, like watch the whole video. Hopefully it'll all come together. I try to do a lot of pictures, and then I'm going to do a lab this week that'll marry up to what we're doing in this PowerPoint. So igniters, pilots, flame sensors. Let's go. So let's start with a flame sensor. So when we light a flame, it's important. Do you agree that it would be important to prove that the flame is there? I mean, think about that. If we didn't successfully light the fire, the flame, the gas, and we allowed the gas valve to stay energized, it would just dump raw gas into our heat exchanger. So could that be bad? Yeah, yeah, that could be bad. Because you could load up the heat exchanger, you could dump raw gas outside. For one thing, you're wasting fuel. And for another thing, it's a safety hazard because you're dumping raw fuel, drawing it through your furnace. And if it were to light some errant spark somewhere, it would cause a great big mess. Probably need a new house after that. So we need to prove that the flame is actually lit and it's burning. So we do that with a flame sensor. And there's different ways to prove that we have flame. And the method is different. So for different types of furnace, different manufacturers, they do use different methods. And you know what? I'm not going to cover them all. You're going to be out in the field someday and you say, hey, I ran into something different. Stuart never told me about this. But think about the process. At the end of the day, we're proving that the flame is either lit or not lit at the time that it's supposed to be lit or the time that it's not supposed to be lit. So the old school furnaces, this is going back to like that 70% efficient furnace. It would be like a natural draft type furnace. Those were very, very simple, simplistic in nature. And they would have a standing pilot, which means there was a little tiny flame, a pilot light, that's basically a smaller version of our burners, and you would physically light it, and I'm going to show you in the lab and stuff, and I've got a video coming up that's going to show you how to do that. So bear with me a little bit. So that little pilot light, oh, I've got a phone call coming in, but I'll just let it ring through. That little pilot light, it's lit and it stays, the little flame is lit 24/7, 365 days a year, unless you physically turn it off and then relight it at the beginning of the heating season. It'll run all summer, all winter. And what it does is it provides a flame. Flame is always present. The flame is always present. And on a call for heat, the gas valve simply opens up. And when the gas hits that pilot flame, that little flame, tiny little flame about the size of a matchstick flame, it lights the natural gas. So how does it work? It's called a thermocouple. There's also a thing called a thermopile. We'll just start with a basic thermocouple principle. And these are almost obsolete. Probably see them mainly like in water heaters and whatnot. Flame rectification, that's another type. That's like what the modern furnaces use. I'll get into that. And UV and IR light, we'll talk about that. So thermocouple, it's used with a standing pilot ignition. Standing pilot means there's a standing pilot. It's lit all the time. It's just a standing flame. And on a call for heat, the gas opens up, hits that little tiny flame, and ignites our burners. Think of it as an electrical generator. Okay, and so here's how that works. It generates, the flame itself comes in contact with a thermocouple, and it generates a small amount of DC voltage. DC means direct current. So it's like a 9-volt battery, or a battery in your car is a DC, a direct current, okay? Versus like in your house or in most buildings and whatnot, it's all going to be alternating current. Hopefully you've learned about that in your electrical class by now. So the heat comes in contact with a thermocouple, and it actually generates a small amount of DC millivolts. Milli means a small amount of voltage. So milli would be 10 to the -3. So that's a 1,000th of a volt. So pretty small. So 31 thousandths of a volt is what that is. And this is how it works. This is a diagram. I've got a video coming up that'll show you what it actually looks like. But this is essentially 2 wires wrapped together, and there'd be a coating around it. You don't actually see the 2 wires like that. But there's a copper wire and an iron wire. They're dissimilar metals. And there's a reaction when heated. So when a heat source, heat source would be a fire. Think of this little orange blob as a fire. And this is coming in contact with my thermocouple. And if I were to measure that across my voltmeter, I should get like right around 30 millivolts on these thermocouples. It's pretty cool. Like, it kind of blows my mind that somebody came up with some of this stuff. Let me see. Here's a video of how this actually works.
Hey guys, this is AC Service Tech, and today what we're looking at is the combination gas valve and thermocouple, and how the two work together in order to hold the pilot on. After you have a pilot lit, you can then turn this gas valve to on, and then you can power between here and here with 24 volts, and then you can get the main burner to light. All right, but as far as the pilot goes, say, you're holding this button down and you're allowing gas to flow through, and you're lighting it, and you have a flame, and it's just, anytime that you let up on this, after a minute, 2 minutes, 3 minutes, the flame ends up going out. Well, that has to do with either the thermocouple or inside the combination gas valve, there's what's called a solenoid. All right, so this solenoid right here is powered by DC millivolts, and you actually are pressing this down, just like this, anytime that you press this button right here, okay? So you see how I'm depressing this right here? Every time that you do that, you're allowing the gas through. So here's where it enters at, and it comes through, and it's allowed to then go down into the main part of the gas valve. The thing is, once you let up on this, you want this to be stuck up, okay? So it allows the gas from here down into the lower portion. So once again, you press this down like this solenoid comes down, and what happens is when you heat a thermocouple rod up, it actually sends DC millivolts through right over to here and into the back of the solenoid. The solenoid has two connections, straight down in the middle and the side. Okay, and the thermocouple has two wires as well. You have the inner wire and you have the outer wire. Here's an example right here. You have the inner wire and the outer wire. And then at the end, you have two dissimilar metals that are welded together in order to connect them. So anytime that you heat this rod up, you're sending DC millivolts over to here, and we're going to go ahead and see how this DC millivolt solenoid works. So we're going to connect this in, and then I'm going to go ahead and heat this up. So what we're going to do is we're going to hold this down, and this isn't much of a flame, but it should be enough. This is a 30 millivolt thermocouple. Okay, so you see that the solenoid is actually holding itself in. All right, we're going to see that this will pop back open again once that thermocouple rod cools down. All right, so now you see it popped open. All right, we're going to do the same thing again, but this time I'm going to disconnect it here. All right, so now it's holding it again, and we're going to go ahead and disconnect it. You see that? So we just loosened it. Let's tighten it again. Hold it in and see how it holds it. Okay, so that's the function of this solenoid along with the thermocouple. Now let's go ahead and check how many millivolts we have anytime that we're heating this up. All right, so you see we have our multimeter set on AC. We want to go ahead and change that to DC voltage, which is the straight line. So we're going to go ahead and heat this up. As we heat this up, you see the millivolts is increasing right there. Okay, this is a 30 millivolt thermocouple. All right, and this is a very tiny flame that you see. So you see that the voltage is going up. It doesn't take much millivolts in order to hold that solenoid in place. So a larger flame would be able to get around 30 millivolts. All right, so that's what opens the gas to flow through the gas valve and to have the continual pilot flame being lit. Okay. After you have your pilot flame lit, you can go ahead and turn this to the on. Then once again, you can just go ahead and power it with 24 volts. The gas will have been...
Okay, so what that video is essentially showing is, remember the inductance, that electromagnet? So basically you're physically pushing that button in, which compresses that spring, and there's enough, that 30 DC millivolts, there's enough inductance, it's like that electromagnet, that it'll create enough energy to hold that, enough magnetism that it'll hold that valve open. So when you push it in, you light it, and it starts to generate a small amount of DC voltage. It creates inductance. So there's a coil inside of here, okay, with many, many wraps, and when that's sufficiently lit, it sufficiently provides enough voltage to create enough inductance to hold that, enough magnetism to hold that open. And as long as that flame is lit, it's generating, and it'll basically, how do you want to say, hold that open until the flame, if it gets blown out from Could be blown out from wind, or it could be loss of gas supply, things like that. So that's basically how that works. And I'll do another lab, go into more detail than this guy did on how that works. But I did want you to see a video of explaining and showing the internals on how that works. So a thermopile is basically a larger thermocouple with more of those two dissimilar wires wrapped together, and that produces about 500 to 750 millivolts. It's like putting multiple batteries in series, and it's basically doing the same thing, though. It's as it heats up, it just generates more electricity. So, and the reason they do that is they'll run this 500 to 750 millivolts. They'll run it through the entire control circuit. So on like a camper or things like that, where you don't have like a readily available like 110 volt power supply, you can light that and that'll run the entire furnace off of the controls anyways, the burner off of your thermopile. So let's talk about flame rectification. So the modern furnaces in our lab, most furnaces use this type of flame sensing. And because the flame, we don't want a standing pilot. It's inefficient, it's not safe, it doesn't make sense. Okay, a standing pilot made sense in the 1960s. In 2020, it does not make sense to do. So we like to, when I call for heat, there's no sense in having a standing pilot because we can light the flame and extinguish the flame on demand because we have the technology. So we use what's called flame rectification. And what that is, and I've got a picture and I'll show you. You guys will actually do this in the lab when you come back. This is really important to know. So there's a wire coming out of our control board. It's a white wire and it sends a small amount of alternating current, 90 volts, to a flame rod, which is just a metal rod. And that's in the stream of the flame. So as the flame comes out of the end of our burner, it comes in contact with a metal rod, which I call the flame rod. The flame rectifies the voltage. Rectification is a process of converting alternating current to direct current. So the flame is actually a conductor. If you think about it, it's unbelievable in a way that the flame is not only acting as a switch. So we send a wire, which is our path, to a flame rod, which is also part of our path. And when the flame comes across it, it's in contact and it comes back through the ground of the furnace. So think of the flame as a switch, which closes from the flame rod to the chassis of the furnace. But it also, in order for voltage to pass through the flame, it can't come through as alternating current. It comes through as DC current. So that's rectification. Rectification is the process of converting alternating current to direct current. It's not just on furnaces. That's a rectification that's used in electronics all the time. But we just happen to be doing it with a flame. So here it is. There's a wire going. Here's that white wire. And it's going to this porcelain shielded wire. So when it sticks through, and when the flame is lit, the flame comes in contact. Basically, the flame acts as a switch, and the electricity passes back through the ground of the furnace back to our control board, and our control board is monitoring that. So, but it comes back as DC current. So there's two things. It acts as a switch and it acts as a rectifier. Here's what it looks like when it's actually in operation. So there's a small amount of 90 volts of alternating current. And see how the flame is actually touching that flame rod. Well, the electricity passes through. And see how the flame is touching ground and it's basically going back to the burner, and there's all kinds of things touching the metal surfaces of the burner, of the furnace of the heat exchanger. So the flame is acting as a path for the electricity, but it's a path that only allows direct current. So, and that's what proves that there's a flame there. When there's no flame, there's no path. It's not a switch. So, uses the flame as a switch. Flame is located between the electrodes. Flame completes the rectification circuit. Rectification circuit converts AC power to DC. Furnace recognizes DC power and opens the gas valve. So, it basically holds the gas valve open. So, we send electricity to our hot surface igniter. Gas valve opens, and it gives it like 5 seconds to 10 seconds, 5 to 10 seconds to establish flame. And once the flame is lit, and that flame rod sees that, that flame rectification, basically the control board sees that there is flame present. It opens the gas valve. It keeps holding it open until the flame is extinguished, and then it locks the gas valve out. It can be used on both spark to pilot, which is sort of like what we have on our rooftop units, or on direct hot surface igniters. That's what it looks like right there. So the porcelain is because where it's attached to the mounting bracket, you want to shield that so it doesn't ground out on that. So that's why that porcelain is there. And then this metal, this flame rod here is basically what's in contact with our flame. Here's a diagram, our control board. This is our white wire. It sends alternating current up to our flame rod. The flame comes in contact with our flame rod. The electricity, DC electricity now, goes back through the grounding chassis of our furnace, and our control board recognizes that there's a flame there. All right, let's talk about ignition. How do we light the furnace? How do we light the fire? So we're going to talk about that next. There's a pilot light and there's direct ignition. Okay, a pilot can either be a standing pilot or an intermittent pilot, and a pilot light is just a tiny little flame. It's a smaller burner than our other burners. Basically a small burner. Standing pilots burn continuously, and an intermittent pilot relights that little tiny pilot light on a call for heat. And then once the flame is established, it'll generally take that pilot light back out. This is what a pilot light looks like, and this is a thermocouple right here. So this is a picture of a thermocouple, and it's holding the gas valve. So this thermocouple is generating a small amount of 30 millivolts DC voltage. That's basically a generator, and that electricity creates inductance and magnetism that holds our gas valve open. When the gas valve's open, it provides pilot flame to our pilot burner. Basically uses a spark or a hot surface. So if you understand how a spark ignition, so sometimes we use spark and hot surface to light a pilot, and sometimes we use it to light our flame directly. Back up. This is supposed to be a video. Let me see if I can get that to work. No, can't get it to work. So if we look at this again, So here's a pilot light. I'll back up again. Watch this video. So our pilot light lit. It's an intermittent pilot, and if you give it a minute here, it's establishing. So it's using that flame rectification process to establish that this is working. And now it's lighting all of the burners. So these are ribbon burners. It's probably a 70% efficient unit heater. Isn't that pretty? Nice, pretty blue flame. I'll skip ahead and the shutdown sequence when the heat demand is satisfied. There she goes. So the flames are going up into a heat exchanger. Air is blowing across the heat exchanger. Okay, there's going to be some worksheets to go with this, and I will be following up this week with some lab videos. So have a nice week, and get a hold of me if you need any help or any questions or anything. We're moving at a pretty good pace, and we're going to do reviews as soon as we get back into our face-to-face lab. We'll review a lot of this stuff face-to-face. So if you have any questions, that should clear them up. All right, take care.